it does not matter which of the 4 exponential functions you had. What is the domain? All real numbers. Okay, let's talk for a second about why that is all real numbers. Okay, if you're looking at the graph, as you move from left to right, there's nothing missing. There's always a y value if you want to look at it that way. The other way to look at it is when you're trying to figure out the domain, the question you should be asking is, if I plug in a number for x, is there any number that I plug in that won't give me an answer? Okay, so if I'm trying to raise, 10 to a power, is there any number power that I can't raise 10 to? Well, no, you can raise 10 to any power that you want to, and you're going to get an answer. So that's why the domain is all real numbers, if you want to look at it from that perspective. Okay, how about the range? How about the range? What was the range for all of them? They should have all been the same. From 0 to positive infinity. Now notice, I put a parenthesis with the 0 because these never actually equal 0. They get super, super close to it. And if you just look at the graph, it kind of looks like it does cross 0 or touch 0 because your graph disappears. But if you keep on zooming in, you'll see that it never actually touches the x-axis. So you can write it this way, or you can just write y is greater than 0, not equal to. You cannot raise 10 to a power and get 0. You can't do it. You can't raise 1/2 to a power and get 0. It's not going to happen. But these are always positive. They do go to positive. Okay, so if it never equals 0, then we don't have any x-intercepts. No x-intercepts. What were the y-intercepts? 0, 1. Okay. All of these, when your x is 0, when you plug in 0 for x, you're raising a number to the 0 power, and anything to the 0 power is 1. Okay. So that's the normal y-intercept for an exponential function. Okay. Now, when we get to intervals of increase and decrease, okay, we kind of have we split this into 2 sets. Okay, 2 of them are always increasing, 2 of them are always decreasing. So which ones are always increasing? Which 2 of these functions were always increasing? E to the x and 10 to the x. Okay, e to the x and 10 to the x were always increasing. So we would write negative infinity to positive infinity. Because remember, we use our x values. So all the way from x equals negative infinity to x equals positive infinity, moving left to right, those 2 are always increasing. So the other 2 were always decreasing. Okay, and so that's still negative infinity to positive infinity, but it's decreasing. And so that was 1/2 to the x and 5 to the negative x. Now, they may not look like those have anything in common, but I can rewrite 5 to the negative x. What do we do with negative exponents? How do we get rid of negative exponents? How do we get rid of negative exponents? We move it to the bottom. So it's 5 to the negative x. So we can move that to the denominator. So this is the same as 1/5 to the x. Okay, 1/5 to the x. So here's something we need to know about exponential functions. When our base is greater than 1, when the base is greater than 1, it's always going to be increasing. When the base is between 0 and 1, it's going to be always decreasing. Okay, so when a is greater than 1, always increasing. When a is between 0 and 1, I don't want to say just less than 1, because less than 1 would imply negative numbers, and we put the restriction on there that it's got to be greater than 0. Okay. But that's something you need to recognize. When you look at the equation, you should know whether it's an increasing exponential or a decreasing exponential. Okay? But be careful with things like 5 to the negative x. It's got to be to the positive x to be able to determine this. So if it's got a negative exponent, you got to put it in the denominator. Or if it was already a fraction. So for example, if this were 3 over 2 to the negative x, okay, 3 over 2 to the negative x, that would look like a is greater than 1, but it's to the negative x, so you flip that over. 3 over 2, let me write that down. Not everybody's is auditory. Okay. If we've got 3 over 2 to the negative x, that is really 2 over 3 to the positive x. So that one is decreasing. Okay, that one would also be a decreasing function. Also be careful, a lot of people want to say if a is a fraction. Be careful with saying that because 3/2 is a fraction, okay? But it's a fraction that's greater than 1. So don't just say if a is a fraction, then it's always decreasing. It depends on whether that fraction is greater than or less than 1. Okay, so if we're always increasing or always decreasing, do we have any extrema, any maximums or minimums? No, we don't, okay? Because remember, maximums and minimums are created when you change from increasing to decreasing. So if they never change, then you don't have a maximum or minimum, okay? Now our end behavior, okay? We've still kind of got them grouped up in these two pairs for e to the x and 10 to the x. Let's talk about its end behavior. So as x goes to negative infinity, where are my y values going for those two? 0, okay? As we go to the left side of our function, our y values are at 0 there. And as we go to the right side of our increasing function, then our y values are going to positive infinity. For the other two, when they are decreasing, then as x is approaching negative infinity, where are our y values going? They are going to positive infinity. It flip-flops this relationship here, okay? And as we go to the right side, our y values are going to 0. Okay, so these are just some properties that you need to know about exponential functions. The big thing I want you to take away is that being able to determine from the base whether it's increasing or decreasing, and the end behavior is also very important as well. Okay? All right, so let's look at this from a little bit more of a function perspective. So if we have the function f of x is equal to 2 to the x plus 1. So we're just adding a 1 in our exponent there. It's still an exponential function because x is still in the exponent, but we're just kind of adding a little bit more to it. And I want to evaluate that at x equals 3. Y'all know how to evaluate? You just plug in, right? So f of 3 is 2 to the 3 plus 1. 3 plus 1 is 4, so 2 to the 4th is 16. And 2 times itself, 4 times is 16. 2 times 2 is 4, times 2 is 8, times 2 is 16. All right, if our function is 2 to the negative x, and we want to evaluate that at x equals 2, we plug in negative 2. You just told me a second ago to get rid of negative exponents, we move it to the denominator. So that's 1 over 2 squared. And 2 squared is 4. So 2 to the negative x at x equals 2 is equal to 1/4. So that would be the y value on the graph. Okay, let's change this to e to the x. If our function is e to the x and we're evaluating at 0, again, evaluate, fancy way of saying plug in. So e to the 0 is 1. Anything to the 0 power is 1, as long as it's a real number, okay? 1 to the 0 is 1. 2 to the 0 is 1. 10 to the 0 is 1. E to the 0, pi to the 0, okay? Pi is a number too, Don't forget, that's not a variable. Pi is a number. Pi to the 0 is 1. I feel like there was something else I was going to say about that. Oh, 0 to the 0, though, we don't know what that is. Okay? We don't know what 0 to the 0 is. It's something called an indeterminate form. Just as a little side note. Okay, so let's review some properties of exponents. Okay, let's review some properties of exponents. We want to simplify these expressions as much as we possibly can using our properties of exponents. So if we have 2 to the x minus 1 times 3 to the x times 2 to the 2x, what do we know about properties of exponents? Like, what can we combine here? They have to have the same base, right? We can only put together the ones that have the same base. So the 2 to the x minus 1 times 2 to the 2x, what do we do with our exponents when we are multiplying? We add them, okay? So just so that it's kind of clear, you don't have to put this intermediate step, but some of you need to see it. You add x minus 1 plus 2x, and that's still times 3 to the x. It has a different base. We can't do anything about it. So if we simplify this, that would be 2 to the 3x minus 1 times 3 to the x. And that is all the simplifying that we can do, or all the simplifying we want to do. We can manipulate that a little bit more, but I'm not going to. Okay, b, we can do the same thing. It just has a base of e. It doesn't change the properties of exponents. The base doesn't matter as long as it has the same base. So e to the 2x minus 1 times e cubed, they have the same base, so we can add their exponents. This time we're combining the constants. So that's e to the 2x plus 2. Now, I don't know that they would do this, but you may see them factor out that GCF of 2, just because you can, pretty much. So just realize that those are the same thing. All right, how about this one? Same thing, okay? We're not changing anything. Properties of exponents still apply. They have to have the same base, so we can add their exponents. Whoops, plus 3. Okay, so that is 4 to the 2x plus 2. Now, I am going to take this one a step further. Okay, I am going to factor out that 2 because I can rewrite this one a little bit more. Okay. Do y'all remember what property of exponents results in us multiplying two numbers? What property of exponent results in multiplying two numbers? Anybody remember? Raising a power to another power. Y'all remember that? Nope. Okay. When you raise a power to another power, okay, like this, okay, if I had 4 squared in parentheses and then I had an exponent of x plus 1 on that, I would multiply those two powers. So I'm just kind of taking that property and going backwards because I know that 4 squared is 16. Okay, so these two things don't look very much like each other, but they are equivalent to one another. They are equivalent to one another. I could check that. I could check their equivalency. I can pick a number for x. I don't know. 5 is usually a good number. Okay, I'm going to pick 5 for x. 2 times 5 minus 1 times 4 cubed. Okay, I get that answer. And then I'm going to plug it into my answer, 16 to the 5 plus 1. And I should get the same number. And I do. Okay, that's one way you can check equivalency. Pick a number for the variable, plug it into the original, plug it into your answer, you should get the same number. Okay, now that number is not the answer because you just picked some value to plug in for x, but it's just confirming that they are equal to each other. Okay, let's keep going. One more, okay? One more, we're going to combine a bunch of properties here. Okay, so we've got bases of 4 and bases of 7. We've got bases of 4 and bases of 7. And it's all within a division problem. So there are a bunch of different ways that I could approach this problem. Does anybody want to tell me what they think that you would do first? Aaliyah? Okay. Okay, yep, let's do that. Okay, let's start by combining those powers of 7 in the bottom. And what happens when we do that? Yeah, we can cancel because there's multiplication in the numerator, there's multiplication in the denominator, so we can cancel those 7s right there. Okay, so what do we do with the 4 to the negative x over 4 to the 2x minus 3? What? Okay, we could, there are two different things we can do. We could fix the negative exponent, we can move that to the bottom, or we can subtract the exponents. I'm going to show you both ways and that they result in the same answer, okay? So if we subtract, okay, I like to do top minus bottom, okay? Now, you got to be careful with that, okay? You have to be careful with that because you've got multiple terms in the bottom exponent, so you've got to distribute correctly. So that would be negative x minus 2x, that's negative 3x, and distribute that negative to that negative 3, that's really plus 3. And if we did what we did in the last problem, let's factor out a negative 3. So we've got 4 to the negative 3 to the x minus 1, which is 4 cubed is 64, so that's 1 over 64 right here. Okay, or if we went with Haley's way, fix the negative exponent. Now you have to be careful with that because your numerator just can't disappear. You got to put a 1 there to hold its place. Then we could add our exponents and we can factor out the 3. And then we've got 1 over 64 to the x minus 1. Now, I can move that x minus 1 out there because there's just a 1 in the numerator. 1 to any power is still 1, so it doesn't really matter. If there was something other than 1 there, then the x minus 1 exponent would just apply to the bottom, okay? It would just apply to the bottom. But since it's a 1, 1 to any power is still 1, so it really doesn't matter on this one. Okay, so same conclusion, two different approaches. Yes, sir. Why isn't the one on the left negative what? Negative 64? Huh? Because the negative exponent just puts it in the denominator. It doesn't make it, it's still positive 4 times positive 4 times positive 4. It's just the negative exponent moves it to the denominator. Okay, so same answer, two different approaches. They're both valid. Whichever one works best for you. Personally, I kind of like this one because I know y'all are going to mess up over here with distributing that negative to the 3. Despite how many times I tell you you're going to mess up and to not mess up, y'all still do it. You don't put parentheses around things and then you don't distribute the negative through the parentheses. Y'all got to get better about that, okay? As a whole, you really do. Okay. All right, let's look at some equations. And let's look at some exponential equations. And I'm almost done talking for a little bit. I'll show you these examples and then y'all get to work for a little bit. Okay, so if I give you the equation, 9 is equal to 3 to the x plus 1. Okay, normally when we're trying to solve an equation, we're trying to get x by itself, which is pretty easy when it's not an exponent, okay? But it's kind of stuck in that exponent right now. So the first few problems that we do here, the goal is going to be, can we write the two sides of the equation so that they have the same base? Because if we can write them so that they have the same base, then their exponents have to be equal to each other. So we have a base of 3 on the right. Can we rewrite 9 so that it has a base of 3? Yes, we can. Oh, we're so confident. 3 squared is 9, right? Three squared is 9. Okay, so we rewrite it. So we have the same base on both sides. So as long as we have the same base, we can just set the exponents equal to each other, and we're going to get the answer, right? X equals 1. It's an equation. Take a second, plug it back in, see if it's true. If x is 1, 1 plus 1 is 2, 3 squared is 9. Imagine that. Okay, now B is a little bit more complicated. So we got 1/2 to the x is equal to 8. Okay, so are 8 and 2 related to each other? Yes. Okay. How? 2 cubed is 8. Okay, so 2 cubed is 8. Now, 1/2. Can we rewrite 1/2 so that it's a power of 2? 2 to the negative 1. 2 to the negative first, that negative exponent would move that to the denominator. So 2 to the negative first is 1/2. Okay? And then we have a power raised to a power, so we multiply. So negative 1 times x is negative x. So negative x is equal to 3. So that must mean x is equal to negative 3. 1/2 to the negative third power is 8. Because I'm over here justifying 1/2 to the negative third. That negative exponent flips our fraction. So that's 2 to the positive 3, which is 8. Okay? All right. So I want you to practice with these.